Well, I want to thank you all for coming. It's a summer evening and the weather's nice and you could be doing other things outdoors, but instead you came to get educated, which I appreciate. So you've heard the title of the talk, and this is the area we're going to be visiting tonight, the Valley of 10,000 Smokes and the scene of the largest eruption of the 20th century, which has occurred in Alaska exactly 100 years ago today. And so happy anniversary, Katmai. The eruption lasted about 60 hours, so it went from June 6th, 7th, and 8th. And what I'm going to do is start out with some eyewitness reports, what people experienced near the volcano, and then I'm going to go to the scientific expeditions and tell you what they discovered and kind of also hopefully give you a little sense of how science works and trying to figure these things out. And then one year ago today, I was fortunate to be part of an expedition that went to this area. They go there every year. In fact, Charlie's boss and my old boss is there at this very minute leading an expedition. They go every year, and I was fortunate to go last year. So we'll have some on the ground, boots on the ground, photos of that, and then we'll end up with kind of a lessons learned and what are we doing today in monitoring volcanoes, particularly in Alaska. So here's a scene looking from the site of the eruption down the Valley of 10,000 Smokes, and we'll come back to this picture later. Well, let's get some historical perspective. What else happened in 1912? Woodrow Wilson was elected president. New Mexico and Arizona admitted to the Union. Fenway Park, L.L. Bean, and the Oro Biscuit make their debut. Japan donates 3,000 cherry trees to Washington, D.C. And, of course, the most famous catastrophe of that year was the Titanic. So I'll tell you now beforehand, that the number of fatalities attributed to the Katmai eruption is 1. So, which is pretty amazing. So we can kind of, in a way, enjoy what happened there without being guilty about a lot of lives lost. Thursday, June 6th, dawned clear. There's a map of Alaska. This is the Alaska Peninsula. The Cook Inlet anchorage is kind of up off the map there. Homer, the big island of Kodiak. There were a lot of Native American settlements around here. And on that day, the mail steamer, the SS Dora, was making her way from one of the towns to the main town on the island. And around 1 p.m., she noticed a giant plume to the northwest, about a mile wide and going way up into the atmosphere. Around 6 p.m., ash started falling on the ship. And the ship then was plunged into total darkness about 6:30. So ship's going along here. The eruption was there. These lines are ash thickness, which kind of jumping ahead of the game, but we'll come back to that as well. In Kodiak, meanwhile, light ash begins falling at 5 p.m., becoming heavy by 6 p.m., and a black night settles down by 7 p.m. And it would stay dark for over a day in the town of Kodiak. And Kodiak had, I think, around 400 residents at the time. Kodiak was 170 kilometers away from the eruption site. I'll let you do the conversion to English. Here's a close-up of the region. So the Native Americans, the Aleuts, had settlements kind of in the interior. They did fishing and hunting. And then during the summer, and again, this was June, they would go to the coast and have fishing camps there. So they had sort of temporary settlements there. Also, the Russians had been in the area since the mid-1900s, and they hired a lot of Native Americans to help them do fishing. And some of them were way down the coast, down here, fishing for salmon and so on. So a lot of the people were gone, actually. So it was pretty, not only lightly settled to begin with, but partly evacuated. This gentleman, Harry Kayak, was 6 years old at the time. He's shown here at age 75. So he was with his family and down in one of the fishing settlements. And this is what he had to say. It was just like this, bright sunshine, hot, no wind. That's when the volcano started. Started snowing like that fine pumice coming down. Made a lot of noise. Kaflia Bay started to get white gradually. Dark didn't come all of a sudden, it comes gradually. Pretty soon, pitch black. So black, even if you put your hands 2 or 3 inches from your face outside, you can't see it. And then this, the children run up the side of the high hill, all hollering, let's go see the mountain, because they had heard this blast coming from the west. One of the children was blind, but he running right by me, he hollering louder than anybody, let's go see the mountain. We get to the top of the hill and see sky get black all over, all full of lightning. Now, in this part of Alaska, they don't get thunderstorms, so lightning was a novelty to them. The lightning was being caused by the ash in the volcanic plume, and that's a very common sight in volcanic eruption. Then our parents start hollering for us to come back to our barabaras, and we run back down the hill. Now, a barabara is like a sod house that these people lived in, so they build an entrance, they pile high with vegetation and moss, and you can see they're actually kind of nicely suited for this kind of catastrophe happening. Now, as soon as it became apparent that a volcano was erupting, one of the village elders said, turn all your canoes upside down because they're going to fill with ash and you won't be able to move them. And get all the water supplies you can under cover. And he knew from even though there had not been an historical eruption experienced in his lifetime, he knew from oral tradition you had to protect your water. You had to get it in away from the ash before the ash contaminated. It gets hot. It got hot in those barabaras. We pull off all our clothes. We soak them in water and put them over our face. Those people who have mosses in their barabara pour water over those mosses and put them over the nose and mouth so they can breathe. After a while, we open the door and try to see out. All black, everywhere. A little bird fly into barabara. He can't see where he goes. We children wash his eyes with water and he stay in barabara with us. And then after 3 days, when it dawned clear, they let the bird go. So meanwhile, in Kodiak, 170 kilometers away, you do the conversion, it was dark for 2 days, and then it dawned clear on June 9th. At least a foot of ash, I can convert that actually, of ash was falling in Kodiak. You can see a guy walking in the drifts. It looks like snow, but it's volcanic ash. Now, you don't have this problem here, but we have snow and it weighs down houses. Ash is many times heavier than snow. So buildings in Kodiak were collapsing due to the weight of the ash. And it doesn't melt away either. You have to physically remove it. People in Alaska have to deal with this periodically as the nearby, especially in Anchorage, as the nearby volcanoes erupt. They do a lot of shoveling, a lot more than we do during our blizzards. And so it became apparent that Kodiak was uninhabitable for a while, so a lot of the people were evacuated on boats to the northeast, away from where the ashfall was. So here's the ash. It did fall in Anchorage, someone asked me earlier. Ash carried aloft worldwide, reported in Virginia on June 10th, Europe June 20th, 27th, and then fine particles went around the world probably many times for over a year. The climate impact wasn't as great as you might expect because this is at high latitude, so it doesn't get quite the dissemination that a Krakatoa would, or even a Pinatubo back in 91. And we'll come back to that. The Native Americans were relocated. So here's the old village of Savanowski where they were living, and they created new ones down here. The people down on the coast boarded a ship and started a new settlement called Perryville, named after the captain of the ship, way down the coast. All right, so the place was pretty much evacuated. I should also add that there was total devastation of wildlife. The salmon, these rivers were rich in salmon until the eruption, and then they were basically sterile. All the wildlife was killed, so there was no way you could live off the land. So a few years elapsed, and finally the first scientific expeditions went in there. And the first well-known one was funded by National Geographic, which funded a number of these in there, led by a guy named Robert Griggs, and I forgot to bring his book down, but we have the book in the library. and it's entitled The Valley of 10,000 Smokes. So here he is right here. I'm sorry, it's this gentleman here, shown with his crew. And as the years went on, he kept mounting more expeditions. They got more money, and they studied a lot more. Here's tents. This guy here, Charles Fenner, was the first geologist to go in here. Griggs was actually a botanist, so he was studying how the land rejuvenated. Fenner was the first geologist. And remember those initials, because we'll come back to that later. But he really formed the first real, the first study and the first real developed thoughts about what happened during the eruption. So this is what they saw. They stood in that valley and they saw hundreds upon hundreds of steam fumaroles coming out of the ground. And that's why they call it the Valley of 10,000 Smokes. Over time, those gradually died out, as you might expect. But at that time, and for at least 10 years, it was quite a sight to behold. This layer here was the first real, this was a different kind of volcanic deposit. It wasn't ash falling from the air. It was an ash flow. So you have ash mixed with hot gas coming out of the vent, roaring down the flanks of the mountain, and going out. This is what happened at Pompeii, and it happened here, but this is the closest we ever got to one really soon after the eruption and could study it scientifically. So this is an ash flow deposit, as opposed to the airfall ash that came down separately. And it's really the best example that we've had in modern times. Here's another picture from the Griggs volume, which came out in 1922. Now, I love this picture because what's going on here? Well, he's cooking bacon. But, so here's the skillet, the bacon's in it. There's no flame. And then notice the size of the stick. He's got an iron skillet, tied to the end of that thing. He's holding it with one hand, So what's going on here? Obviously, the gas is rushing out of here. In fact, he was holding that down. So it was hot gas. Not only you can cook the bacon with one hand using that contraption. These guys would go out on a trip and, they'd make bread dough and put it next to one of these fumaroles and come back for a loaf of baked bread. This is another amazing sight they have beheld, a brand new volcano, Nova Rumpta. And they called it a plug of stiff lava. Today we know this is a volcanic dome. And here it is wreathed in its own ash all around it. So that was a discovery by this group. Obviously the Native Americans no one could get near it for such a long time. They didn't really know what was going on there. So this was an entirely new discovery. And another amazing discovery, a volcano 6 miles away, Mount Katmai, which is your classic cone-shaped thing, the roof of it completely collapsed in and made this giant crater with a lake in it. Today we call this kind of thing a caldera. So it was obvious, we know there are many examples of these around the world. When these collapses occur, that's usually the magma chamber empties out, comes out the sides of the collapse, and then the roof caves in. Again, there are many examples of this. See, it was naturally assumed that this was the source of the ash that came out during that big eruption. The bottom here, which is now flooded, they looked down and they saw this thing. This is a partially breached, a little dome. And it was never seen again because the lake filled with water because of all the abundant rain there. Actually, it stayed exposed for a few years, but soon enough it was submerged, and that's our only evidence of that particular phase. So a little bit of lava turns, well, I'm getting ahead of the game, but that's our only evidence in hindsight that anything came out of Mount Katmai. And we'll go into that some more. So there were two main types of deposits recognized. This ash flow top, or ignimbrite, that's the mixture that roared out of the vent. And it welds, because it's so hot, the little particles weld from their own heat into solid rock. And this is, now you can cut a gorge in it like the Grand Canyon. And then the other main type of deposit is the airfall ash, which forms these nice thin kind of sandy layers, and that's loose. You can dig in this stuff. This stuff is harder to dig in. But as you go downward in it, you get earlier in the eruption, and it gets more and more welded. And this deep canyon isn't even at the beginning of the welded stuff. You're only looking at about, I don't know, the top third of the entire thickness of this ash flow top, which we now know to be over 600 feet deep. This guy was called the Glacier Priest. He was a Jesuit priest who taught at Santa Clara University in California. And I guess he studied glaciers, that's why you know. But he came here several times. He brought his students and dogs, and he made some early observations. So the result of the early expeditions, these were their conclusions. Most of the ash erupted from Mount Katmai, that collapsed volcano, because that's what usually happens. And lesser amounts came from the Nova Rupp event, that's that volcanic dome we looked at. And also little vents in the Valley of 10,000 Smokes, VTTS. So that was one of the early conclusions. The mountain collapsed by melting of its own magma, so it sort of ate outside its own innards, collapsed, and then the magma came out in the form of ash. Now there was a peculiar thing, and I'll show pictures of this later. Banded pumice, white and black, lava mixed together in these clasts that came out, and that was they thought that was a mixture of the new magma, which was the white stuff, and the old rock, which was the black stuff, and we'll revisit that because that's actually a central part of the story. Also, to produce all those fumaroles in the Valley of 10,000 Smokes, there must have been a heat source underneath, which they hypothesized. One scientist thought there was actually a big granite body underneath the whole valley, sending up heat and making those fumaroles. Another guy, Dr. Fenner, that we saw a picture of, thought it was a thin sill, a sheet of magma underneath the valley doing that. More recent scientific expeditions, the first volcanologists did not arrive in the area until the 50s. And these guys had looked at a lot of volcanoes. And they knew better how to deal with the evidence for this than Briggs, the botanist, or Fenner, kind of the general geologist. And then here's a more recent expedition. Of course, they've been going continually because this is a fabulous laboratory. So they came to different conclusions. All of the ash erupted from that Nova Rupta vent. You started out with rhyolite, which is a high silica, very white ash. And then you eventually got to andesite, which is a very dark ash. So rhyolite first, about over half of it, and then going to these other less silica-rich things. And we'll come back to that. But it all came out of that vent. The magma chamber, though, was under Mount Katmai and traveled horizontally 10 kilometers, 6 miles, to erupt at the Nova Rupta vent. Emptying of the magma chamber due to that lateral plumbing caused the mountain to collapse. This is still something that they wrestle over today, what exactly was going on here. Why would you have a process like that? The fumaroles in the Valley of 10,000 Smokes were powered by leftover heat in the ash flow sheet itself, not any underlying magma. All right, so here's a view looking northwest. Here's the Nova Rupta dome. That's that lake plug. And so we know then that the main vent, shown by the circle, was about this big. And all that ash came out of there, and a lot of it roared down the Valley of 10,000 Smokes in the form of one of these roiling ash sheets and buried it to 600 feet and went all over the place. Elsewhere, a giant column of ash went high up in the atmosphere, probably at least 100,000 feet, and spread ash eventually around the world. And here's the valley. Okay, another view. There's Nova Rupta, the vent area, and there's Mount Katmai. And this odd feature here we know is the turtle. So let me back up a bit. Here's the vent. So ash came out in the very end, kind of the coarser chunks, couldn't go very far, and they form what we call an ejector ring around the vent. But it's not symmetrical, it's asymmetric, kind of in a northward direction. And one of the early volcanologists called this the turtle, and we'll visit that on the ground. For some reason, not necessarily wind, it ended up depositing mostly in this area. And then as the vent kind of collapsed inward, faults formed, and it kind of sagged, it slumped a bit. So that's what these are. These are faults from the slumping. Most of the airfall ash went to the east over towards Kodiak. That's because the prevailing winds were coming from the west. So somehow, though, magma got from Mount Katmai way over here to this vent. Here's a nice aerial view of the Katmai caldera showing the collapse from the air. And then this is kind of neat view along the edge because these lines in the rock are glacial striae. Well, that means you must have had a glacier above this rock, moving down the mountainside, grinding that rock and forming those streaks. But obviously there's nothing there now but air. So it's a nice illustration of what used to be there. Obviously there was enough summit above it, 2,000 or 3,000 feet, to have glaciers up there that were coming down the side of the mountain. So what processes were occurring during the eruption to produce the great variety of volcanic rock? So they were starting to figure things out by the mid-50s, the general thing. But there was a lot of other work to be done. There's a lot of funny stratification in the ash flow tuff. There's a lot of compositional breaks going on in here. Just a lot of different things. So the task from then on has been to really try to get into the mechanics of the eruption, figure out exactly what went on, what processes were occurring, what was the timing, and so on. So the geologists have been occupied with that task ever since. So I mentioned the variety of compositions. So we had rhyolite, very white. That means it's high in silica, this, like a quartz mineral. And then as the eruption progressed, you got gradually less silica-rich, and you end up with andesite, which is very dark. But then you also had this peculiar banded rock. And so you see that in this layering here. You start out down below, it's lighter colored. This stuff came out first. This is the airfall ash we're looking at. It was silica-rich, rhyolitic. Then it got darker, it became another composition intermediate called dacite, and then andesite. Now these compositions here are kind of typical for arc volcanoes, and I haven't really gone into plate tectonics much, but this is a typical volcanic arc setting. Pacific plates diving under Alaska, and these volcanoes are forming a chain along the edge. We have the same situation in the Cascades of the western U.S. But why was there such a great diversity of lava compositions? So to understand this, you've got to do a lot of dirty work. And I kind of liken it to CSI, the TV show. They come to the scene of the crime and they've got to do very painstaking work to figure out what's going on. In this case, it meant studying these pumice and ash deposits in great detail, sorting out different sizes, what sizes are represented at a given distance, what compositions were they, and so slowly unraveling, sort of indirectly, what was coming out of the vent during the eruption. So you have something called stratigraphic analysis, and you can make a correlation. So here we are 4 kilometers from the vent, and this is airfall ash. You're seeing only the upper half of it, and it's this thick, and you can break it into different layers doing that painstaking sieving and hand lens analysis. And so these are separate eruptive events coming out from the plume. And then you had a hiatus here where there was a pause in the eruption, that dark line, and then eruption continuing. But each one of these layers is a slightly different composition. So once you know that, you go 30 kilometers away and find the same layers. Notice we have a person for scale here and a Swiss Army knife for scale here. But they're the same layers. It's the same event. That's how you piece all these things together and figure out what was happening over a large region. You can also take the rocks and make very thin slices and look at them on the crystals under a microscope. The crystals are moving around in the magma chamber, and you can kind of get a sense of what history they were experiencing by studying the zoning of them. Some have different compositions inside than outside. In older volcanoes, they have radiometric elements that you can then date in the thousands or millions of years. Of course, we know the exact date of this, so we don't need to do that here. But that takes a lot of microscope work back in the lab. So you bring your samples back and do this kind of study. So here you're actually trying to figure out not what was going on the surface, but what was going on down below in the magma chamber before the stuff even came up. And we can do that. So, and then you can do kind of basic chemical analyses of all your samples. So this dashed outline here is what the older lavas do. Their compositional spread. You don't really need to worry about what this is. Calcium oxide, it's just one element. But silica, that's that important thing that tells you whether it's light or dark. The light colored stuff up here would be over at this end. These high numbers, that's the range for rhyolite, and down here at these low ends, that's the range for andesite, the darker stuff. So the older lavas in Mount Katmai occupy a zone like that. And that's pretty much normal for a volcano in this setting. Here are the compositions of the pumice pieces that came out of this eruption, and they kind of occupy it. But a peculiar thing happened. They stopped here, and then you have to go all the way down to here, the very high silica. This is the first stuff that came out, the high silica rhyolite, the really white stuff. It came out of the vent first. There's a gap in here. And we've been fighting over the significance of this gap ever since this was discovered. That's not typical for volcanoes like this. You should not have an outlier of a much higher silica composition lava coming out that is also mixed, coming out at the same time or nearly the same time as this. So let's kind of put it all together. This is the eruption of Mount Pinatubo in 1991, the second largest of the 20th century. And we can imagine that the plume for Katmai Nova Erupta looked very similar, probably as big or bigger, rising up into the sky, and just immense. And you have two processes going on, like we've discussed. You got some ash carried up buoyantly with hot gas going way up into the atmosphere. That eventually produces our airfall ash, those nice layers. You got some ash that comes up, but it's entrained in gas going sideways, and it comes out and makes those ash flow tufts. So kind of two paths for the ash coming out. And here's a cartoon from this eruption. So you have ash and pumice going way up into the air, being carried in some place, situations long distances, and then ash coming out, ash and pumice coming out and hugging the ground in one of these ash flow mixtures. So this is kind of the picture that was put together. At the beginning of the eruption, that's when all the ash flows occurred. Okay, so the Valley of 10,000 Smokes was created during the first 16 hours of this 60-hour eruption. Flowed down the ground, wiped out everything, just scoured it clean like a Brillo pad, and laid down all those hundreds of feet of ash. At the same time, the plume was going up and was depositing these layers that we can now correlate through that careful work I mentioned. So you have A and B, and then you had, then there was a hiatus, and the ash flow deposition stopped, and you had airfall from then on. So these are layers coming out. They're different because the compositions of the lava coming out of the vent were changing over time, going from lighter to darker. And here are those layers over here. And this correlates nicely with what they experienced in the town of Kodiak, 170 kilometers away. So they were noting when they were getting ashfall. They didn't get, of course, any of those ash flow tufts. Those were confined near the vent. They were getting the ashfall, and then there was a hiatus, just like we found in this stratigraphy near the vent. Then there was more ashfall, called episode 2. That's episode 1, episode 2. Then a hiatus. That's that thin layer E I showed you in the picture. And then ash continued again, and then ended on June 9th, and that's episode 3. So there's a nice correlation here between the eyewitness accounts in Kodiak and what they found in the layers near the volcano. And here's another slide. I haven't mentioned the earthquakes, but how many seismometers were there in Alaska? 1. And it was 1,000 kilometers away, 600 miles away. However, the earthquakes were so large that it recorded a lot of them. They were 6s and 7s, which is very big for a volcano. There was a lot going on. So here's a chart showing the earthquakes that were recorded and how they think that correlates with the events at Mount Katmai. So the collapse of that mountain probably generated the biggest earthquakes, as you might expect. Beginning of the collapse, and then there's a main collapse. Here's a bunch of 6s and a 7. And then some other processes, maybe, I don't know. The earthquakes went on for months and years, actually. I don't know, some kind of settling going on at the volcano or something. But the main ones were probably associated with the collapse of Mount Katmai as the magma chamber was drained. And then here again is the airfall ash record at Kodiak. So these diagrams, these summary diagrams, kind of tie it all together. So now we know that this eruption emitted about 3 cubic miles, should be 13 cubic kilometers of magma. If you took all the ash that came out and compressed it into solid rock, you come up with 3 cubic miles of rock. That makes it the biggest eruption in North America. The second biggest was, in the 20th century. The next biggest eruption that we've studied well is Krakatoa, a little bit earlier and a little bit smaller. The gentleman who introduced me tonight, Charlie, has studied this. Now, this is an island in Indonesia, so most of the ash went into the ocean. So Charlie here is the first volcanologist to actually don scuba gear and dive underwater and study the deposits from Krakatoa. And this one obviously is more well known because so many more people were affected. Tens of thousands were killed. There was a tsunami. Lots of things were happening. Again, in Nova Raptor, we know of one person who was indirectly killed, and that was an elderly woman who was suffering from respiratory problems, and the ash got to her, so she passed away. But no known other deaths from that eruption. It's pretty remarkable. Here's Pinatubo, a little less than half the size of Nova Raptor. Vesuvius, we all know about. And there's Mount St Helens, a puny 0.1 cubic mile of ash. In 1815, Tambora exploded, another island in Indonesia. That was about 10 times as big as Nova Raptor. That killed about 70,000 people, and that severely affected world climates. The following winter was called the following year was called the year without a summer, and it affected much of the globe. This could happen again. In fact, some people are modeling climate change scenarios. What can we do to slow down global warming? And they're coming up with schemes to inject particles in the atmosphere, kind of modeled after what volcanoes really do. And here's what we know at the vent. So all that ash came out of that vent, which is kind of a funnel shape. And then finally at the end, the magma, which is down below, all the gas has been released from it. So it's kind of this stiff magma. And it comes out as indeed a plug. And it oozes out and then comes to a stop. So what do we have left to learn? Well, there's that pesky gap in lava compositions. So this is what we're arguing about now. Why do you get that? And why do you have banded material? Well, the people who study this most, volcanologists Wes Hildreth and Judy Fursky, they picture a zone magma chamber under Katmai. All the models have the chamber under Katmai because that's where it collapsed. And here, it's red here, but this would be the white stuff, all right, which kind of comes as a froth to the top. And then you have dacite, which is this yellow, and andesite, which is the gray. So if you erupt this from the top, then basically you get the reverse order. The red stuff in this diagram will come out first and lay down. Then you would get the yellow, and then you would get the gray. So they postulate that a sill is kind of a horizontal sheet of magma, came out and then broke through up at Nova Rupta to create, the main eruption there. Well, my erstwhile boss and Charlie's boss doesn't like this idea because the rhyolite that came out is too different from the other rocks. You can't explain that gap by fooling around with one magma chamber. The rhyolite is too different from the other layers. He has to have another source. That's what he believes. So in his model, here's Mount Katmai. That's the mountain that collapsed, and here's the vent. He has a dike. Now, a dike is a vertical sheet of magma, as opposed to a sill. That came up from below, and that dike was of rhyolite, that white stuff that came out first. The sill intersected both the area of the vent and the magma chamber at Mount Katmai, but erupted here. So this is the initial eruption. This is layer A. This is the lower part of the ash flow top. And they, triggered the eruption. Then, as it waned, the magma here actually is more dense than the magma in this vertical dike. So it actually wants to fall down. It actually wants to sink into this. This is dacite and andesite, the darker stuff. It wants to sink into the rhyolite magma, and then the currents or something propel it over to here and bring it out. In both these models, there's kind of some stretching going on here, okay? It kind of suspend belief. It's a difficult thing to explain. And I don't know, I'm sure they're going to argue about it for a while until we do more studies. Now, does Katmai do anything today? Well, it certainly does. There's so much ash there that windstorms, and it is very windy there, are capable of carrying ash around today, almost as much as a volcanic eruption in Alaska in some cases. So here's the satellite image from September 2003, long after the eruption, showing how much ash is carried up into the atmosphere. And I think you can get murky skies in Seattle and Vancouver based on this. Some people think this is an important process for fertilizing the ocean. So plankton actually thrive on this. It's like, reseeding the ocean or composting the ocean. It's an important nutrient source. So let's go on to the travelogue portion. Every year since, I think before 2005, John Eichelberger of the USGS, formerly of University of Alaska, and Pavel Izbekov have led a team of students from the U.S., Russia, and international to Katmai for a 9-day expedition. And I was lucky to go on it last year. Here's our group. So we have Americans, Russians, Germans, one Brit, and one Chinese. And that's our group photo. And you have to fly into this place, as most places Alaskan. You fly over kind of typical tundra-like. There's a moose in that picture somewhere if you can find it. And you land at Brooks Lake. And you cross a floating bridge to Brooks Lodge. And this is our Brooks Camp. So this is now part of the National Park Service. And this is world famous, as you'll see in a minute. There's one of the cute cabins. If you want to go here as a private citizen, I think it's $400 a night. We got a price break, and of course I went as part of my job, so I didn't pay it. There's pumice floating along this lake, and I couldn't sample it because guess what? It's a national park. But if you go there, you see pumice, white pumice from the eruption floating along the shore. It's pretty cool. There's a view kind of in the direction of the Valley of 10,000 Smokes, Lake Naknek. And here's the world famous Brooks River, which is 1 mile long, connects Brooks Lake to Naknek Lake. Why is it famous? Because there are rapids right there. And if you come a month after we were there, you see this. And there's a viewing platform and photographers from all over, and I'm sure you've seen pictures and movies and so on. Because the brown bears make their migration. The salmon start to run in late June and July, and the brown bears migrate to the spot from many miles away and do fishing. And so there's an elaborate procedure there. The Park Service, you have to go through training. You have to be able to recognize when a bear, they use a cutout, is 100 feet away, you know, and what do you do and so on. So you can be pretty close to these. Of course, you're on a viewing platform and watch them in relative safety. But you might encounter them somewhere else. Well, we had to make do with this guy, this little juvenile golden bear who, notice he was wandering through camp. I encountered him on a trail later. You just be cautious and keep your distance, you know. And then for the expedition, you have to put on a backpack. Here's mine, and because it's cold, I had to bring a lot of winter clothing, so I weighed in here at 55 pounds. And to get to the Valley of 10,000 Smokes, you have to wade across Swift Creek, and it's not terribly easy. One of the reasons why we go this early is that the meltwater, that creek starts to rise, and it gets harder and harder in July and August to cross. So for safety reasons, we cross early. And it's not Swift Creek, but I'm blanking on the name. Anyways, you have to cross it. So, and you get across, and you can look back, and here's some of that ash flow sheet, about as far away from the eruption as it was. This is the very tapering edge of that 600-foot thick sheet. And it's sort of slightly welded. It's got nice columnar joints in it. And above it is a veneer of airfall ash. So we're going across this plain. This is all pumice here. And there's the Valley of 10,000 Smokes. Hardly any vegetation in sight. And then you come up, and here's a canyon cut in that ash flow top. It's actually not even totally welded here. It's partially welded, and then below the creek level, it gets really welded. And then there's airfall ash on top of that. Another view showing ash flow top, partly welded, and then airfall ash draping that. So this flowed out over the ground, and that came from the plume overhead. And another view, creationists, if they could get in here, would love this place. Why? Because this canyon was cut in, 100 years or less. So there's a lot of processes that occurred very rapidly here. They could go to town if they were able to get in here. Fortunately, it's remote. Here we're hiking across. Okay, so this is what's left of one of those fumaroles. This brightly colored rock is where steam was coming up, and the steam was carrying chemicals with it, elements. The red is iron, the yellow is sulfur, but there were things like copper, zinc, molybdenum, so on and so forth. So it was like, they're all like miniature ore deposits. And they were beautiful because they were all brightly colored like this. And they were scattered across the landscape. But 100 years ago, that had a steam vent coming out of it. Now we're at the upper end of the valley. Notice that this stuff is a lot darker. That's the stuff that came out later, the ash, and this is ash flow top. This is actually hard. We're actually deeper in the section too. Well, we're not deeper in the section, but this stuff is welded more. You can see black chunks in it. So this would be andesite, and there's airfall ash on top of it. And this is our camp. This is called Baked Mountain Huts. I don't know how long they've been up there, but it's a lifesaver when you get up there because you need some solid structures because when the wind blows, it blows hard, and it's like sandblasting. So you get inside these things. They're just the crudest of structures. But okay, there's the outhouse. The old one blew away a few years ago, and they helicoptered in a new one. You can't see it because of these metal cables holding it in place. Because try to pound a tent stake in this, it won't work. You have to use rebar for tent stakes. You have to use something about this long. This is another reason why we come in June, because there's still snow up there, and you use the snow mound. You stick a pipe in the snow and get your water source. It's the only water. Otherwise, you'd have to hike several miles to that creek, which is muddy and churning. Here you get fresh snowmelt water. So every day we had a bucket brigade going over to that little pipe, which is just dripping out. and getting water for cooking. And we're going on our first hike here. Here's the turtle again, that funny deposit right next to the vent. You can see it's kind of cut by, scalloped by faults. Here's Professor Eichelberger explaining how this is a volcanic bomb. It came out of the vent hot, still hot, and then landed. And it's explaining how that happens. These things kind of expand like baking bread as they come out. And there's Nova Rocket. Again, this is that last plug that came up, but the vent is, much bigger than that. In fact, it kind of ate away at this mountain, which was called Falling Mountain. If you go there, you can hear there are landslides occurring here constantly, There's a big chunk of the mountain collapsed into the vent during the eruption. So that's why it's Falling Mountain. So we paid a visit to the dome. Now remember that geologist, that 1923 geologist that I showed you a picture of? I don't know if you can see it here, but there it is, 1923, and there's his initials. And there's a whole bunch of geologists that carved their names as they came. That became a tradition. If you came here on a scientific expedition, you came to this particular chunk of the dome and you carved your initials in it. Of course, now it's a national park. They kind of frown on that kind of thing. But it's nice graffiti to look at. Climbing the dome, which is about 500-600 yards or feet long and about 200-300 feet high. Climbing up some more. So this rock, as it comes out, it gets cold and brittle and then breaks up as the thing oozes out more. The surface of the dome kind of just crumbles, and that's why it's so broken looking. And you can see here, it used to be kind of a coherent flow deposit. There's the layers of the lava. It's sort of like obsidian, if you've seen chunks of obsidian. This stuff was not quite that silicic. This is one of the students, Ronnie Gravethan. He's from Germany. This is a very precise GPS unit. He was going there to set this up temporarily as a station to measure any kind of changes over like 3 days. And this thing, is precise down to the millimeter or centimeter. So he wanted to see if there was any swelling going on, and he could also compare it to any measurements they had a few years ago. Now, my pack was about 55 pounds. Ronnie's load was about 135 pounds, because he had to carry that thing as well. And he's also 7 feet tall. We gave him the Paul Bunyan Award at the end. It's a lot easier to get down the dome than it is to get up it. Here's another view of camp. This was my tent I stayed in for 8 nights. That's Mount Griggs, named after the early explorer. And the night before, we got snow just above us, not quite reaching camp, fortunately. These are the jugs of water where that's what you carry over the snowbank to get water. Charlie, you'll be here someday. On the bad days, of which we had about 2 or 3, everyone crams into one of the huts, and Professor Eichelberger gives a lecture, which he loves to do. In fact, John is leaving the USGS this fall to go back to University of Alaska, because he's really an academic at heart. And I think he had a good time here during his 3 or 4 years, he really missed the students. And you can tell that when we were on this expedition. He just loved to lecture. Almost too much, if you know what I mean. Going out on another hike. So we had day hikes from this hut. You backpack in 9 miles, stay at the huts, and then we did forays out for 8 days. Each one was about 9 miles, but you only had to carry a day pack. So here's some airfall ash in the upper valley. And here's one of the gorges cut by creeks, again, just in the last 100 years into the welded ash flow top. Who knows what that is?
Brown bear.
That's the brown bears making their pilgrimage. There's the forepaw and the rear paw. So we were supposed to keep our eyes out. I never saw any. But they would come over the pass, Katmai Pass, and these were fresh, of course, because there's no rain dropping. But this bear is heading towards those falls and those salmon. Here's one of the seismic stations. This is a permanent station. No longer do we have to rely on an instrument 600 miles away. We have a bunch of them, and I'll show you a picture of the network. And we're visiting one here. Even outside we had lectures. John brought his whiteboard. You couldn't get away from it. I wanted to pitch the damn thing. This is a picture I took of patterned ground. This is what you get when you get freeze-thaw. And this brown gunk is probably the most abundant life in the area. It's kind of a lichen, it's algae, fungus, mixture of kind of a lichen, a brown scum that forms on the surface. Hardly anything growing here.
What's the scale?
Each one of those things, thank you for asking. If I can go back. I don't know if I can go back. Yeah, each one of those squares is about a foot. Here's a close-up of pumice near the vent. Beautiful, multicolored. Just an art shot. What's this shot of? Well, here's a tree. A little spruce seedling. It's the only tree we saw pretty much in 8 days. So it's struggling to, get a foothold here. And you can see it's going to be a long time before any kind of soil really develops. And there were a few pioneer plants that you might expect. Some shrubs. I forget what that is. But that's a tree. And our big day was not a 9-miler, it was an 18-miler. That was to hike up to the rim of Mount Katmai and back. Now, remember, in June, it never gets dark here, so you never had to worry about it. You could take all day, literally all day, to get to your destination back. I mean, we got back from this at, I think, 11 o'clock at night, but who cares? So we're making our way to Mount Katmai. There's another one of those fossil fumaroles. Hiking up the mountain on the edge of a glacier. So this is the south flank of Mount Katmai. We're making our way slowly. And it was a blizzard at the time. Here we are at the top. You're supposed to look out and see that glorious caldera, and we just saw blowing snow. But everyone was enjoying themselves nonetheless. Now, in another year, you might get this view. And you can see the caldera in the background. The lake sort of freezes over, but even when we were there, there's always a little patch of openness because there's still magmatic heat coming up out of the volcano. Even though it wasn't the main source of the eruption, there was something going on.
How deep is the lake?
Pardon? Oh gosh, it's hundreds of feet. I don't know the figure now, but it's hundreds and hundreds of feet. When you come back from this 18-miler, you get a day off. So that's when we took the advantage to dry out our clothes. And the students get their turn lecturing. So everyone was supposed to bring a presentation, and I did too. Everyone else is sitting around. Here's a view south of Mount Majik from where the snowbank was. And then on our last day hike, we went up to Katmai Pass. And I split off with another guy. This guy is Gary Freeberg, who's a noted landscape photographer. If you go down to Harrisonburg, he has a studio, and he teaches. He's an adjunct professor at James Madison. So he and I took off on our own and got away from the group for a while. In the background is Baked Mountain. These strata are the old rock. That's not even volcanic. That's Jurassic, which is about 200 million years old, siltstone, and shale. That was what we call the country rock in this area before Nova exploded. The Nova erupted event dome is right just off the picture here. So it plastered that mountain with ash, and that's why it's called Baked Mountain. So on my last hike out there, I hiked up this thing, which looks worse than it really was. So I hiked up that spur, and here we are. Here I am getting near the summit. And everything was going fine until I got up here, and then I was hit with 60-mile-an-hour winds at the top, and I literally had to crawl down the other side. I was afraid I was going to get blown off. And here's the view from the northwest spur. There's Baked Mountain, and there's the Valley of 10,000 Smokes. So you can picture how this used to be. Nice U-shaped glacial valley, now completely filled in and no trees growing. So that's the ash flow tuff, roared down the valley. Here's the airfall ash draping the mountain that came down later. Now tonight when you go home, if you go to Earth Science Picture of the Day, you can Google that or Google ePod, you'll see this picture. I submitted it and they put it in for the anniversary. How big is it? Well, let's see. It's 9-mile hike from here. We started around the corner. So I don't know, we're probably looking, I'm going to guess, 6 miles to the other end here. And then, a mile or 2 wide. Does that sound about right? At least a mile wide. So finally we get back to Brooks Camp, and the Russians and Germans are very good at Monopoly. And the way you get out is the way you came in, you fly. Alright, so much for that. It's running late, so I'll wrap this up quickly. What will be the impact of a Mount Katmai eruption today? Well, there's obviously more people in Anchorage. There's not a whole lot more people in Kodiak. And the other area is a national park, so that's likely settled. But the ash went over a large distance, but the real answer is, what would the biggest impact would be air travel. Anchorage, you may not realize it, is a major hub between the U.S. and Asia, particularly for shipping. So FedEx, I think it's the second largest FedEx shipping hub in the world. So these flights come in and out of there. You can imagine the impact then, the chaos a large ash eruption would cause on air travel. Remember in Iceland in 2010 what happened? Europe was shut down for a couple of weeks. Well, that scenario would play off here, and that ash would, keep going and certainly shut down airports, probably in Alaska, and maybe affect far down as, California. But that's really what we say now, that no volcano is truly remote. Because even in the remote Aleutian range, there are passenger jets flying over to and from Asia over all the time. Any eruption can have an impact on air travel. Here's a picture of one of these FedEx 747s coming in. There's Mount Spur volcano in the distance. It erupted in 92, shut down the airport. To the right, north, is Mount Redoubt. It erupted in 2009, shut down the airport. And they were tiny eruptions compared to Katmai. How about monitoring these volcanoes? We have a lot more seismometers out. Each one of these blue triangles is a seismometer. You might say, what warning? Obviously, we had no warning back then of an eruption. Will we have warning today? Yes. Probably days, maybe weeks, even months. Okay? Because the magma starts to move up to the earth and it makes earthquakes and starts jiggling and so on. So the area is now well monitored, as is most of the Alaskan volcanoes and most of the U.S. volcanoes. They have a lot of instruments on them, particularly seismometers. GPS can detect swelling, and we'll have advance warning of this. However, a cautionary note, there's a number of earthquakes. And we have satellites, so we can tell when a plume has erupted. The darkness here is related to temperature, so it's cold, which means it's high altitude. This is the Mount Redoubt eruption. And so we pick that up in satellite, 45 minutes later. A cautionary note, this is the Alaska Peninsula. Katmai is down here. We have instruments there. We have instruments over most volcanoes. We did not have one around this one. This is called 4 feet. It wasn't on our list of active volcanoes. So, of course, in 2006, it erupts. Well, it burst. It blew out a plume of ash and gave us a big scare because we weren't prepared for that at all. We had no instruments around. And when we fly over it, we saw a line of fumaroles in a line, about a mile long, kilometer long, describing what you would call, yes, a dike. So, without any warning, and with no instruments really nearby, a dike of magma came up in an area we weren't expecting, and, blew off some steam. It then chilled off, and nothing's happened since. But that tells us we don't know everything there is to know. It's the active volcanoes, sort of like keep your enemies close or something. The active ones, you know what they're going to do, okay? It's the surprises that are going to get us. The caldera that hasn't erupted in 1,000 years, and it's going to produce the big one. So we always have to be on our toes, and it just means be vigilant. So here's an end shot here. The Russian ladies asked me to pose with them, and people like to give me grief because notice after this arduous 9-day hike, they look fresh as a daisy. Me, not so much. If you want to read more about this, you can download, and I think there's a flyer on this, so you can download a really good report that just came out, tell you everything you want to know, and it's quite readable even for a non-volcanologist. I mean, it's scientific and technical, but it's not totally opaque. Then National Park Service put out something, a centennial volume, and that has some of those witness things that I told you about. That's a chapter, and that's where I got that material from the Native Americans. Visit our websites, and there's useful information here, anniversary page. I think that's a handout, and I want to thank these people for helping me out. Thank you.